Okay, we start a new topic. Part B, smoothness rule and Fibonacci numbers. Part B.1, reduce problem size by half. All right, first, let's look at the problem. Our problem number 11, count binary digits. The problem is very simple. Now, given a positive decimal integer n, find the number of binary digits in its binary representation. We know we can write this n, the regular integer, the form we are familiar with, but now we like to write it in the binary representation. I think you know the binary representation. After we write in the binary representation, then you count the number of bits in your binary representation. Let's try to solve this problem. Binary digits problem. All right, let's do some simple analysis first. First, let us review the binary representation. From your discrete math, you have this background. Okay, given decimal integer n, we can write it in the form of this one. Here, all these b's, they are the binary digits. They are the binary digits. Okay, only 0 and 1, because the base is 2. Here, the binary, so the base number is 2. Then each binary digits or bits, right? Binary digits, that's the bits. Okay? Each such either 0 or 1. But we also know for the highest bits, it cannot be 0, right? The most significant bits cannot be 0. Otherwise, if it is 0, we do not use this position. Okay, we can reduce the position number by 1. Okay, that means the highest bit number is 1. Okay, Other than this special highest one, the remaining bits could be 0 or 1. All right. Now, based on the problem requirement, the answer should be s plus 1. Here, s, our subscript from 0, 1 through s. So if you count the number of bits, that total number is s plus 1, not s. Okay, But if we can find the s value, then we can find the answer. So that's not a, very straightforward. But our question becomes, given integer value n, we need to find the s number, in the representation, standard binary representation. All right, so that's the, the background of this problem. Next, we need to find a solution. Insight, the most important property of this problem. We want to find it. That is the insight. How to get insight? Here, the way we used here, we used before. So you may still remember that. Let's see. Use a transformation to change the structure. Transformation. Okay, remember in our polynomial evaluation problem, Horner's rule, we did that. Polynomial transformation, right? Yeah. Here we do another transformation. Oh, in another problem, we also use GCD, the greatest common divisor. When we do integer division, right, using the division algorithm, we also use certain transformation. Here, we need to do another transformation. Yeah. All right. Here, from the structure here, you can see base 2, power of 2, multiplication, a lot of multiplication. Here you can see when we do division, we can change its structure. So the division operation. Yeah. So let's take a look at the division operation. That's the critical step. When we do division by 2, both sides, what would happen? Both sides. But this division should be integer division. Okay? Integer division. Yeah. The fractional part we need to throw away. So we only do the integer division. Yeah. We get this new formula. Okay? Left-hand side, we use the floor function n over 2. Yeah. Because we only want to take the integer part. Yeah. Then the right-hand side, you can see, let us compare the right-hand side with the original representation, right-hand side. Can you notice some difference, similarity? Right? So that observation is important. So we need to catch that and we can find something interesting. Yeah. All right, observation. First one, the least significant bit is removed, right? So B0, when we do the transformation, it is gone. Okay? So that is the first property. Yeah. It could be useful. Yeah. Second, the number of bits is reduced by 1. Total number of bits. Yeah, because the first one is gone. Okay? The remaining still there, right? So when you count the number of bits, you only minus the first one, the least significant one. Okay? Yeah, second observation. Third, the problem size is reduced by half. Yeah. Here we're talking about the problem size. Here, remember, when we discussed this concept, problem size, there is one special case. The problem size is the magnitude of the number. Okay? Magnitude. Magnitude. Right? The magnitude. Yeah, here, we use that problem size. It is the magnitude of this number. So then you look at here, divided by 2, floor function, the size reduced by 1/2. Okay, approximately 1/2. Yeah. But it's a very close. Yeah. So from all these observations, then we can derive important recurrence relation. Yeah. All right. So in our recurrence relation, we use a special function, bin rec of n. Yeah, just give it a name. Yeah, that give us the meaning of this. Given problem size n, magnitude. Okay, this function returns the number of total bits. That's what we need. Okay, so based on this definition, now you can see if we need to find this value, we do transformation here. After you do the transformation, because your problem size reduced by 2, and to get total number of bits in this new problem, you need based on the definition, this function with new magnitude of the problem size, right? Yeah. And the difference, remember the difference is B0, that 1. So you add 1. Okay? So that's straightforward. That's the recurrence relation. Okay? We derive it. Okay? But we need a base value, base case value. This function of 1 equals 1. Okay? Yeah, 1. The magnitude is 1. Yeah. 1 bit. That's simple. Yeah. Next, we need to solve this equation. Okay? So the next question is how to solve this recurrence relation. Okay. Before we go there, here, because this recurrence relation is very straightforward, so we can write a code implementation easily, right? Yeah. So based on the definition, yeah, we can write the basic implementation easily, yeah, like that. Yeah. All right. So you can find the answer in this way, but for this question, we want to derive the formula for it. If you use your program to solve this problem, given n value, you can get an answer, but you do not get a formula for the answer, right? Yeah. You can get an answer for a specific given n number. Yeah. Okay. Yeah. But here we want to do more than that. More than that, we want to find the answer mathematically, a formula. So in that way, it will be even better than using a program to find the answer. Okay? But the most important thing of this is we want to use this problem to introduce an interesting rule. It could be useful. Yeah. Later we have the similar situation. It could be useful. Smoothness rule. So that's the reason. Okay. Yeah. All right. Next, we want to solve this equation. Yeah. Right. First, let's try to understand this equation a little better. First, we can see division by 2 in computer internal CPU implementation. It is a left shift operation. You shift the decimal point 1 position to the left. Okay? Left shift operation. Okay? Yeah. And for the computer internal implementation, that operation is very fast. Yeah. Shift position, so fast. Okay? So, yeah. But here, we also have addition operation. After you do shift operation, you need to add 1, right? Addition operation. That addition operation, so usually slower than shift operation. Here, let us just use addition operation as the basic operation. Slower, yeah. Although, when you have shift operation, you also have an addition operation, 1-to-1 correspondence, right? So we only need to use 1 to count that number. Yeah. Here, for convenience, we just use the number of additions. Yeah. All right. So let me use the new function a of n to represent the number of additions we need to solve this recurrence relation. Okay? Yeah. All right. In this way, we get a new recurrence relation. So very close to the old one. Yeah. Because when you reduce the half by size, you only need 1 more addition, right? you plus 1. You only need one more addition. Reduce the problem size by 1, but you only add one more addition. For the base case, let's assume 1 addition. Okay, probably you can argue we don't need addition, 0, right? But you can also interpret as 0 plus 1, right? 1 addition. Although you can save that, but the difference is not big, just 1. Okay, all right. So let us solve this new equation mathematically. All right. When we solve this new equation, how to handle the floor function? When you look at the formula here, we feel the floor function is not very easy to handle. Okay, the floor function, it is quite, not very convenient. So that's the main part we need to consider. All right. So let's look at the floor function, the property of the floor function. When n is even, 1/2 of the n. But n is odd, you need to do n minus 1, then divided by 2. That's the property. All right, but we need to use the floor function many, many times. Think about when you evaluate this function recursively, you need to apply the floor function many, many times. Okay. So here we need to choose some strategy. How do we handle floor function many, many times? So we need to use a good strategy for that part. The strategy is, we used that before, start with a simpler case. At the beginning, we want to work on the simplest case first. After we get an answer, then we want to see if we can solve the general case. So that is the typical idea. All right. What is the simpler case? Here you can see, compare these two cases. N is even. This case is simpler, because in that case, you don't need to consider fractional part. So that is easier. So we want to take this case first. Okay, all right. Next, this question. What do you wish to have? Because when you have freedom to choose which case is simpler, you want to choose the one that is as simple as possible. So we ask this question. What is your wish? Right? Definitely you wish to have the simplest case, right? So here we use that way to ask this question. What do we wish for this case? The first time we use the recurrence relation. We wish n even. Then no fraction when we do division by 2. Nothing to worry, right? Our first wish, but it's not enough. We need to apply the recurrence relation another time. So our second wish, we wish n over 2 also even. Okay? Because that's the best case. At this point, when we have freedom, we want to choose the best case. Okay? And we want to have all the nice properties all the way down to the bottom. So what's that? So whenever we apply the recurrence relation, we wish the problem size is an even number. The current problem size is an even number. That's the best case we can have, right? Based on that assumption, so we can assume our n is power of 2. If we make that assumption, now you can do division by 2 all the way down to the bottom, the base case. You never need to worry about the fractional part, right? So that is the best case we can get. Yeah. So let us just work on that best case and solve the problem. After that, let us worry about, harder cases. Yeah. All right. Yeah. This time, let's solve this recurrence relation, but we make our assumption n is power of 2. Okay? Yeah. So this time you can see, in order to represent k in terms of n, we need to take a log base 2 function. Yeah. So it's okay. Yeah. All right. So we take it. Yeah. Then let us rewrite the original recurrence equation. So this time we will have power of 2 as the parameter of the function. Yeah. So you can see we get that. All right. So with this new recurrence relation, yeah, now I think we have the confidence to solve it. Okay, so let's do the work. Yeah. First equation we list there. Second equation, problem size reduced by half each side, right? And so on. We keep doing. Every time we reduce the problem size by half from the left and the right, both sides. Keep going until we reach the bottom. And because we reach the base case. Yeah. So we stop. After that, let us add all these equations, both sides. How about that? Okay. So that's the common way we use to find a solution. Yeah. Because you can see both sides, there are many, two sides, they have some common terms can be canceled out. Okay. Let us do the cancellation one by one. Okay. This term cancel out. Okay. One left, one right, we do the cancellation. Similarly, another cancellation. Okay. And so on. All the way down. At the end, you can see the top left term cannot be canceled out. The bottom right term cannot be canceled out. Okay? And it is 1. All right. How many equations do we have? Can you see that? Can you count that number? Yeah. So remember, in the very beginning, I introduced a counting technique. Counting by reference. Count by reference. Here, this equation we associate with 1. So each equation we associate with the superscript, right? The last one associated with k. From 1 through k. So there are k equations. Okay? Each equation, the constant term contribute 1. K equations, the constant terms, the contribution is k. Okay? So you can see k plus 1. So the answer is k plus 1. A of 2 to the kth power equals k plus 1. That's the solution. Okay? Yeah. Let us go back to the original expression, because original expression we use the problem size n. So we need to go back to the n representation. Yeah. So the result for this particular case is A of n equals 1 plus k, because that's the k part. Okay? Okay, we write it in terms of n, so log base 2 of n. Yeah. We know this is a special case where n is power of 2. Yeah. All right. So we solved the special case. What's next? Right? Now we need to worry about the general case. For the general case, before we try to solve it, can you make a guess, right? In problem solving, you will see guessing is a very important step. Guessing is very important step. Here we need to do the guessing. But when you do the guessing, you need to do some reasonable guess. You cannot do the baseless guess. You need to have some base. This is our base. Okay? So we do not do the baseless guess. We do reasonable guess. So the reasonable guess is, okay, from there, a of n equals 1 plus, because usually for the general case, this number is not integer, right? Not an integer. Okay, how to convert it to integer? Here with our guess. We don't know if it is correct or not. Our guess is we take the floor function. Someone may argue why you do not take the ceiling function, right? Ceiling function, we can also get a integer. Yeah, it's possible. If you want, you can take the ceiling function. Yeah. But based on our intuition, we feel floor function should be better than ceiling function. Why? Because here we use the floor function, right? Here we use the floor function. So by our intuition, here we should also use floor function. Right? You can imagine if here we change to ceiling function, right? Is it possible? Later we create a new equation and we use ceiling function, then probably this side you also need to use the ceiling function, right? Yeah, that kind of, we need to use some intuition. So we do not want to do the random way, right? The random way, All right, so that is the first part. Second part, we will verify this guess. You're not done yet. After you make the guess, you need to either prove it or disprove it. If you disprove it, you need to think about, can you modify it to make it correct, right? Yeah. So you have a lot of things to do. All right, in our next video, we will do that hard part. That is the hard part. All right, so let's stop here.